All right, this section we have a couple of concepts we learn. One is basically the definition of a perpendicular bisector. Definition of a perpendicular bisector. And the perpendicular bisector, if you just break it down into the two words that make perpendicular bisector. Perpendicular bisector just means, is anybody watching or are you all just working? I don't know. Okay. Maybe turn your computers around so I can talk and make sure that we're listening. Okay. So a perpendicular bisector, if I'm looking at this segment, okay, bisect means what? Split into two. So it's going to go through the midpoint of this segment. And perpendicular means it's going to come at a 90, right? At 90 degrees. So perpendicular bisector. Splits that segment in two at a 90-degree angle. Okay? The first concept in this section is the fact that if I were to pick a point anywhere on that bisector and just connect it to the end point of these segments, I could do another set somewhere else. Doesn't really matter. Okay? But you can get the idea. I could pick any point on this bisector, connect it to the endpoints of the segment, and because this is a perpendicular bisector, those segments I just created are equal. Those segments are equal. Okay? So this and this are equal. Well, what does this kind of triangle look like? Yeah, but it's called isosceles triangle, right? When the two sides are equal. And so what this tells us is if I know it's an isosceles triangle, then the line that goes from the vertex to the midpoint of the opposite side is perpendicular. Or if I'm told this line is perpendicular, I know it bisects that base automatically if it's an isosceles triangle. Okay, so it goes back and forth. If these two are equal, this is the perpendicular bisector. If this is the perpendicular bisector, then those two sides are equal. Okay. The next concept that we're going to learn in this section is something called a point of concurrency. And in the next 4 sections, we're going to learn 4 points of concurrency. And a point of concurrency in a triangle is a point where each segment that intersects at that point has the same characteristics. Okay? So if I draw, and it might be easier even if I use an app on the computer, but okay. If I draw the perpendicular bisector of this side, and I draw the perpendicular bisector of this side, doesn't have to go through the vertex. It's just got to bisect at a 90. That one's a little off, but and I draw the perpendicular bisector of this side. This is called a point of concurrency, where all 3 perpendicular bisectors meet. Okay, notice that one of these actually went through the vertex, the other 2 didn't. Okay, so they don't have to go through a vertex. The important thing is it's going through the midpoint of that opposite side at a 90-degree angle. Okay, whether it goes through the vertex or not is just coincidence. Okay, where all those points meet is called the circumcenter. That's the point of concurrency of all perpendicular bisectors of a triangle. Say that again. The circumcenter is the point of concurrency of all perpendicular bisectors in a triangle. Okay, and it has an actual, if you know where the circumcenter is, it happens to be, if I were to draw a circle around this triangle, the circumcenter is the center of the circle. The circumcenter is the center of the circle. Okay, it's circumscribed around that triangle. And the point of concurrency of the perpendicular bisectors is the center. So given that, we all know what a radius of a circle is, right? Okay, if I were to draw, does everybody see that that is the radius of this circle? A poorly drawn circle. It doesn't look quite circular, but pretended that it's a circle. Okay, and it's going around this triangle right at the vertex of each at each vertex of the triangle. The red line I just drew from the circumcenter to the vertex is the radius of that circle. Do you see that? So what does that tell you about the three lines? They're equal because they all have the same measure. They're all the radius of that circle. So the circumcenter is the point of concurrency of all perpendicular bisectors in a triangle. Once you know the circumcenter, you know the distance from the circumcenter to each vertex of that triangle are congruent. Okay, so as we go through these sections, what you're going to learn is how to create the point of concurrency. What's used to create it. In this case, it's the perpendicular bisector. And then once you've created it, what other information you know because you know that point. Okay, so we use perpendicular bisectors to create a circumcenter. Once we know the circumcenter, then we know all the links from that circumcenter to the vertices are congruent. Okay, so you may get a problem on big ideas that tells you this point's the circumcenter, this leg is 3. What's this leg? 3. Because you know that the circumcenter is equidistant from the vertices. Okay, one of the harder questions in this section is trying to find the point of concurrency, the circumcenter, if you're given 3 points that make a triangle. Or 3 points that make a triangle. So I thought I might do an example to show you the process of how to do this, okay? Because you're going to have to do this on big ideas. Let me just give 3 points. I have no idea how this is going to work because I'm making these up. So we may end up with fractions, and I apologize in advance. Okay, so what it wants me to do is find the circumcenter, the point that's the circumcenter of the triangle that has these 3 vertices. 1, 1, 2, 3. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. And, okay, that's not going to work. Let's do -1, 6. 1, 2, 3, 4, 5, 6. Okay, there's my triangle. I'm going to connect them. And I'm trying to find the circumcenter. Trying to find the point where all the perpendicular bisectors intersect. So the strategy, when you're trying to find a coordinate where things intersect, all you really need are 2 lines to intersect. Because if I do the math right, it doesn't matter which 2 lines I pick. As long as I have 2 and I set them equal to each other, I know what that point is. Okay, so I'm not going to find the perpendicular bisector of all 3 sides. I'm going to find the perpendicular bisector of 2 sides, find the line of that bisector, and then set that line equal to each other, those 2 lines. That's my strategy. Okay, so we know the definition of perpendicular bisector is it intersects at the midpoint. So I'm going to pick one side, and it doesn't matter which. I'm just going to go with this one. Okay, this point was 3, 7. This was 1, 3. This was -1, 6. So I'm going to pick this side. If it goes through the midpoint, I need the midpoint formula, right? To find the midpoint. So 3 plus 1, 4, divided by 2, is 2. 7 plus 3, 10, divided by 2, 5. So the midpoint happens to be at 2, 1, 2, 3, 4, 5. There's the midpoint. Now I need to create the equation of the line that goes through that midpoint at 90 degrees. So who remembers the relationship between 2 lines that are at 90-degree angles as it pertains to their slope?
Opposite
inverse. Opposite inverse. So if I can find the slope of this line, the opposite inverse is going to have the perpendicular slope. So to do the slope, 7 minus 3, 4. 3 minus 1, 2. So my slope is 2 of this line. So the slope of the line that's going through this bisector, this midpoint, is what? -1/2. Okay, so I know it's going to look like this. And it has to go through the midpoint. So this is the point that I'm going to use to plug in here for x and y. The midpoint. Because my line that I'm trying to come up with the equation for is going to go through this midpoint at a slope of negative 1 over 2. So it's the same as going up 1 over 2, up 1 over 2. So it's going to come in kind of like this. That's my perpendicular bisector. I'm trying to find the equation of that line. Okay, so I found the slope of that line, negative 1/2. But now I'm going to use the point it goes through, the midpoint, to plug in for x and y. So I just plug in 5 equals negative 1/2 times 2 plus b. Well, 5 equals, that's negative 1 plus b, so b is 6. 1, 2, 3, 4, 5, 6. Looks pretty close to the y-intercept. Okay, so my equation is y equals negative 1/2 x plus 6. That's the equation of this perpendicular bisector. I just repeat these steps for one more side. I don't need to do all 3 sides, just do 2. Repeat these steps for one more side. So let's put this one, midpoint, negative 1 plus 1, 0. 6 plus 3 is 9 divided by 2. 9 halves, 4.5, whatever. 0, 1, 2, 3, 4 and a half. So there's the midpoint of that side. The slope of this line, 6 minus 3 is 3. Negative 1 minus 1 is negative 2. So it's negative 3 halves. So that means it's going to be positive 2/3 to go through the perpendicular bisector. So y equals 2/3 x plus b. What's my y-intercept? Yeah, it just happened to be the midpoint was right on the y-axis, which tells me that 4.5 or 9 halves is my y-intercept. That was nice. Does everybody see that? Okay, so I have 2 equations now. Where those 2 equations are equal is my circumcenter. I'm going to go ahead and go up to, so this is actually going to go through there. So this is the point I am looking for. Okay, so to find it, I'm going to set these 2 equal to each other. I find the 2 equations, and then I set them equal to each other, and this is how I'm going to find the circumcenter. Okay? A trick here to get rid of my fractions, multiply everything by what?
2.
Think again.
3.
Think again.
6.
6. My common denominator. You see I have a 3 and a 2 in the bottom? Okay, so I'm going to multiply everything by 6 just to make my life a little easier. Okay, so watch this process as I go. 6 divided by 3 times 2. Okay. I could go ahead and do 6 times 2 divided by 3. I still get 4. But what I always do when I multiply this by 6, I know I'm going to be able to cancel the denominator. That's the point of doing it. So I'm going to go ahead and do that shortcut first. 6 divided by 3 is 2 times 2 is 4. 6 divided by 2 is 3 times 9 is 27. 6 divided by 2 is 3 times negative 1. And 6 times 6. Okay, now I've cleaned it up. It's a lot easier to deal with. They're equivalent, but now I don't have any fractions to mess with. So I get 7x equals, what is that, negative 9? 36 minus 27. Told you it was going to be ugly. So the x-coordinate of my circumcenter is 9/7, just a little over 1. I'm going to just go back up and check. There's 1, a little more than 1, pretty close. My lines aren't exactly straight, but it's in the ballpark. Okay, if I know x is 9/7, how can I find y? Yeah, plug it to either one of these. Y equals negative 1/2 times 9/7 plus 6. Negative 9/14 plus 6. Common denominator, what's 14 times 6? I don't know. Top of my head. 84. So I have negative 9 plus 84 over 14. 84 minus 9 and over 14 is 75 over 14, which is 5.4 about. 1, 2, 3, 4, 5, a little more. So 75 over 14 was the answer for y. The ones in big ideas aren't going to be these fractions. So the coordinate of the circumcenter is 9/7, 75 over 14.
There's only 2 questions that have that on it.
Yeah. So if you get to those two, I have recorded this. You get to those two, you might just turn this recording on and then follow my steps the same time you're doing yours so that you can understand each step and figure out what to do. Okay? I'm going to hand out this graphic organizer that you'll be able to use during this chapter. Okay? The one we're talking about today is the third row down.
Thank you.
Thank you.
So look at this organizer real quick, just so you understand how to use it. The segment name is the perpendicular bisector. The definition is the perpendicular line for each side's midpoint. The point of concurrency for the perpendicular bisector is called the circumcenter. Then there's a figure of what the points of concurrency look like. Okay, point location, and I think, if I remember right, there is let me go home here. Something I gave you guys in the chapter to kind of play with the circumcenter, the point of concurrency of the perpendicular bisectors. Let's see if I can find it, because it's kind of a cool visual. If I don't have it in here, I'll just pull it up real quick. Let's see. Was there a link to something? I don't think so. I'll pull it up. Okay, here is a tool that I just pulled up of how I can change the triangle and what happens to the circumcenter. You see, here the circumcenter is inside the triangle. Here, the circumcenter is outside the triangle. And do you see how this is still the center of the circle that intercepts those vertices of the triangle? Whether it's inside or outside, it's still the center of that circle. The circle just gets smaller or bigger depending on, but it's still, that point is still where all the perpendicular bisectors intersect. Okay, so the point here is the circumcenter could actually occur inside, outside, or on the triangle, depending on the vertices of the triangle. But no matter what, it's created by those 3 perpendicular bisectors, and no matter where the circumcenter is, so if I put it outside the circle, the distance from the circumcenter to each vertex is still the radius. It's still equidistant to each vertex, no matter where it is. Okay, so if you look at the thing I just handed out, we're still talking about the third row. Notice that if the triangle is acute, the circumcenter will happen to be in the inside of the triangle. If it's a right triangle, the circumcenter happens to be the midpoint of the hypotenuse, right on the triangle. And if it's obtuse, it's outside the triangle. And once you know where the circumcenter is, it is equidistant from each vertex. So the distance from the circumcenter to each vertex is the same. And then if you were to draw the circle around it, you can see in that last figure that it actually, the circle intersects each one of the vertices using that circumcenter as its center. Okay, so this third row is what we're focusing on in 5.2. All right, that's it.